Good afternoon, ladies and gentlemen. It's my great pleasure to chair today's seminar, which is devoted to Jindřich Nečas, who was a great personality in Czechoslovak and Czech mathematics, in particular in nonlinear analysis. His work was mostly connected with the Mathematical Institute of the Academy of Sciences, where those who are on site are here now, and with the Faculty of Mathematics and Physics of the Charles University. And I would like to ask Mirko, Rokyta, the Dean of the Faculty of Mathematics and Physics, to tell us some basic things about Professor Nečas and his career. Mirko, please.
Okay, thank you. I hope you can hear me through this device. Of course, not you here in the hall, but somewhere on the net. So this should be something like short introduction to Jindřich Nečas, but everybody who is here probably knows Jindřich Nečas. What is worth remarking that the photo of Jindřich Nečas is not the usual one with the bird around the face. And also you can know the date that today is exactly 20 years that we say goodbye to Jindřich Nečas. This short introduction of mine, I hope it will work, or maybe I will use some more not advanced technique. Okay, maybe I need a technical help. Just on the first slide. Okay. Okay, now it's working. I'm not going to tell the whole life story of Jindřich Nečas, maybe just a few facts that can be of some interest. The first fact that he spent his master's study doing mathematics in years 48 to 52, that it was not on the Faculty of Mathematics and Physics, but on the Faculty of Sciences of Charles University in Prague. And the reason is very simple. The Faculty of Mathematics and Physics was founded in the year 1952. So just in the year when Jindřich Nečas finished his master's study. Another maybe interesting fact is that he finished something what we today call PhD studies. Somewhere here. Before 1990 for some political reasons. So you still see the big gap between the PhD and full professorship. I'm sure that he would be the full professor in a normal country much sooner. It was already mentioned that he was employee of the Czechoslovak Academy of Science and Faculty of Mathematics and Physics. But if you look through his CV, he was also employee of the Faculty of Civil Engineering for a short time, and at the end of his life also the professor of Northern Illinois University, when he has a position of presidential research professor. As to his scientific achievements, it would be a long talk if my aim was to touch all the details about his articles and monographs. Maybe 12 monograph is still quite unusual number, even for today's professors. And of course, more than 140 scientific papers. What also students admired is that he, besides the monographs, also has written 8 textbooks for the students, which is also very nice. But what can be said about Jindřich Nečas in general is that he was the founder of the Czechoslovak and also the Czech School of Modern Method of Investigation of both initial and boundary value problems for partial differential equations. Considering the linear theory, there was the key book of Jindřich Nečas, La Méthode Directe, which was fortunately also translated to English, which is maybe something like 10 years ago. Yeah, it was published in Springer. For nonlinear theory, it is worth mentioning 2 monographs, one with the Fučík, Souček, and Souček's brothers on spectral analysis of nonlinear operators, and of course the introduction to the theory of nonlinear elliptic equations, published in Teubner text zur Mathematik in 1983. I remember when I was doing my PhD and I was preparing for my PhD exam, then Jindřich Nečas told me, okay, so you read this book and tell me something about it. I mean, which part of the book? And he said, okay, the whole book. It's an interesting book, you should read it. So I read it. Also, the continuum mechanics was of his interest. Maybe the monograph which is worth mentioning is Mathematical Theory of Elastic and Elastoplastic Bodies, together with Ivan Hlaváček, and maybe he touched also the relatively modern notions of measure-valued solution in this monograph published in '96 in Chapman and Hall. So if I go to main interests of Jindřich, it surely were regularity of solutions to partial differential equations, together with studying the counterexamples and structure of signatures. These 2 topics were closely related. Also, he was drawn maybe by Professor Polášek and Hlaváček to the topic of continuum mechanics, and also developed the nice theory of multipolar fluids, which are partial differential equations, so to speak, considering higher order viscosities or higher order velocity gradients, if you want. And of course, he was also very interested in Navier-Stokes, and he used to tell us this joke that mathematician studying Navier-Stokes, what he is doing Monday, Wednesday, and Friday, he's proving regularity. Tuesday, Thursday, and Saturday, he's trying to prove blow up. And Sunday, he prays that somebody proves if it is blow up or regularity, at the best himself. So this question is maybe from the blackboard or whiteboard from the Heidelberg seminar, where he was talking about self-similar class of solutions to Navier-Stokes, and still thinking about what is the right answer, blow up or regularity. And as far as I was told, to his last day, he still was discussing this with Vladimir, for example, Šverák, this topic. So this was just a very short overview, and I will just, at the end of this presentation, want to show some pictures. I didn't put the name under the picture, but some of you may guess the man on the left. Maybe you know his spaces. Yeah. So he met Sobolev and were discussing with him. Here you have another picture with Sobolev and with Professors Marek and Kufner, which are closely related to the Czech community. This is the Professor Polášek who drew his attention to continuum mechanics. Also, you may remember the late director of the institute, Professor Jaroslav Kurzweil, who passed away recently. And of course, Jindřich Nečas was always, where there was a good company, he was in the middle of it. So this is just before they start to sing. I remember that moment. I have no picture of singing them because I was just singing together and not able to join. And it's also worth mentioning that he was always smiling and feeling good in the presence of nice women. One of them is here, or even more women. So this is the picture when we were celebrating, I think his 65th or something like that birthday on Paseki school, and all women put themselves together to make a picture with Jindřich Nečas. So what to tell about him at the end? He was a very passionate lecturer. He was gesticulating, he was telling jokes, he was saying, showing us what is happening on the roof of the building when something is, some gradients and so on, so on. So this is how I remember him. And I also remember him as a great singer and a man who liked to sing very much and very loud. But not to finish, just showing that Nečas was in the middle of the women and in the middle of the singing people. He was also, of course, a distinguished scientist, and this is one of his highlights of his life when he got from the President of the Czech Republic, Václav Havel, the Order of Merit in year 1998. So this was a short introduction to Jindřich Nečas, and the picture on the first slide was replaced by the picture as we remember him. And thanks to Honza for providing me this picture. So that's all. Thank you for your attention.
Thank you very much, Mirko. And we will continue with the scientific program. The first speaker will be Dallas Albritton, who is former PhD student of Vladimír Šverák, so therefore he can be considered as a grandchild of Professor Nečas. And Professor Nečas was a certain period discussing the question whether the Leray-Hopf weak solutions to the Navier-Stokes equations are really unique or non-unique. So he would be glad to see the final answer, which we all will hear in the lecture of Dallas Albritton. Dallas is now in Princeton, and after finishing his PhD in Minneapolis, he spent some time in the Courant Institute and then at the Institute of Advanced Studies in Princeton. So Dallas, please, you can start.
Thank you very much for the kind introduction, and I'm really honored to give this seminar on the 20th anniversary of Nečas's passing. So just to confirm, everyone can hear me? Okay, I don't hear any complaints. So if I get some nods from the audience that you can hear me. Okay, very good. So I'll be talking about joint work with Elia Brua, who was a postdoc with me at the Institute for Advanced Study. He'll be moving to a permanent position in Italy, and Maria Colombo, who is at EPFL in Switzerland. So I really appreciate that I could show a couple pictures that were not from the Nečas Memorial website, which maybe everyone has been to, but if you haven't, it's really nice. Unfortunately, so my advisor, Vladimír Šverák, had some remarks posted on the website, but they're in Czech and I haven't been able to read them. I've always been a little disappointed by that. I haven't successfully used Google Translate on it. But in any case, so yeah, as was mentioned, I was a student of Vladimír Šverák, who obtained his PhD in 1986 from Charles University with Nečas. And Vladimír went on to, well, I mean, of course, he's still active and still takes students, but so far he has had 18 students, the first of whom is Taipen Tsai, and I'm the most recent. So though the picture that I found of them together is from Nečas's 60th birthday, 1989. Some of you may have been here. Here's a very young Vladimír And here's, of course, Nečas. So, okay, on to the content of the talk. So we'll be talking about incompressible Navier-Stokes, and I won't spend too much time introducing the equations, but here they are. The unknowns are the velocity field U and the pressure P. And we'll incorporate a body force on the right-hand side. This F acts everywhere in the fluid. It can accelerate and decelerate fluid particles, and it'll play an integral part in today's story. I just want to review a little bit of the theory. Many of you know, but I probably think about Navier-Stokes every day, and not everyone here, I don't know, has that luxury, say, or chooses to think about Navier-Stokes every day. So let's review a little bit. So in 1934, Leray published his seminal work in which he found, which he proved into existence theory for weak solutions of the Navier-Stokes equations. Leray didn't include the body force, but it's really elementary to incorporate it. So let's incorporate it. A modern version of what he proved is the following. For every initial data in L2, which is divergence free, and every body force in L1 time, L2x, there's a global and time Leray-Hopf solution. So we say Leray-Hopf, recognizing also contributions of Hopf in 1951, who proved an analogous theorem in bounded domains. These solutions, they belong to this regularity class, L infinity time, L2x, intersect L2 time, H.1x. And this simply means that the left-hand side of the energy inequality is finite. Why energy inequality? Since for smooth solutions, this is really equality. You get it by multiplying the equation by U, integrating by parts. Well, it's inequality because these solutions, they don't have to be smooth. I mean, we don't, if in general, when you start just from L2 initial data, you're not starting with regular data, so you can't take for granted everything about smoothness. So inequality is what arises naturally in the proof when you use lower semi-continuity to pass to a certain limit. Okay. There's a refinement of Leray-Hopf solution called suitable weak solution. This was a notion, this particular notion was introduced by Käferle-Kohn and Nirenberg in 1982. And these solutions, they are required to further satisfy local energy inequality. This is a local version of the inequality we saw on the previous page. And when the body force F is nice enough, well, let's say F is 0, then these suitable weak solutions have partial regularity. This basically says singularities cannot accumulate on a curve in space-time. It says the one-dimensional Hausdorff measure of the set of singularities of the velocity field is 0. Now, I want to say just a little bit about why Navier-Stokes is difficult. One way to think of it is that Navier-Stokes has this one-parameter scaling symmetry, and those of us who work on semilinear PDEs know that with the scaling symmetry, know that the scaling symmetry plays a really important role. So here's the scaling symmetry. If I have a solution U with body force F, I can form a new solution U lambda with force F lambda by this transformation. This transformation arises. Well, you don't have to get it by guessing. You can derive it using dimensional analysis. In the dimensional analysis, X has dimensions of length, and time has dimensions of length squared. And this is because nu, the viscosity parameter, which I've hidden, has dimensions of length squared over time, and you treat this as kind of dimensionless. Now, the spaces which are invariant under the scaling symmetry, we sometimes call them critical spaces. They play an important role because if you start with initial data in a critical space, that initial data is on the borderline of the standard well-posedness theory, where you treat the nonlinear terms like a perturbation. And let's just look at a heuristic, which kind of tells us that everything's borderline. Let's just say that the velocity field U is like sigma over x. Sigma is some constant, it's a parameter. Sigma is a size parameter. You plug this into the equations, into Navier-Stokes, and you just ask which term formally will govern the evolution. So you plug it into the Laplacian term, and you get sigma over x cubed. Again, this is just formally. And you plug it into the inertial term, U grad U, and you get sigma squared over x cubed. Now, sigma over x, it almost misses the Lebesgue space LD. It's really in the Lebesgue space weak LD. And for initial data like this, these terms are exactly in balance. And when the size parameter sigma is small, in the language of dimensional analysis, we would say that this is small Reynolds. Then the viscous term will dominate and everything should be smooth. When the size parameter is large, the inertial term should dominate because it's like sigma squared. And then one cannot really say what happens. So here's the cartoon picture for what's going on. Let's just say you start with some really nice initial data. Sobolev space H1, but let's just make it smooth and compactly supported, as long as it's divergence free. Then you start evolving by the Navier-Stokes equations, and instantaneously there's a smooth solution. The viscous terms have the regularizing effect. It's a parabolic equation. Everything becomes smooth. And while the solution is smooth, all of the weak solutions, those Leray-Hopf solutions, they all agree with the smooth solution. There's only one solution while everything is smooth. We call that weak strong uniqueness. And you keep evolving until something happens. What could happen is that the solution could lose smoothness. So let's call T star the maximal time of smoothness. And one of the Clay Millennium problems is, can T star be finite? Can smoothness be lost in finite time if you start with smooth data? So we don't know whether this can happen. It's obviously a difficult problem, which many smart people have tried to solve. I forget which days of the week that, all days of the week except Sunday, Sunday on which you pray. Here we can say something about what must happen if smoothness is lost. We can say that there needs to be points around which the velocity wants to become infinite. The fluid wants to travel with infinite speed. We call them singular points. And partial regularity says these singular points, which I've denoted with red X's, they don't accumulate on a curve in space-time. That's partial. Or they're one-dimensional Hausdorff measure is 0. Okay, so let's just say, for the sake of argument, that this situation does occur. You do have loss of smoothness. Then you can continue the solution as a weak solution. And one reason you might care about this a lot is because you want to use the Navier-Stokes equations to model real fluids, and you want to use them to make predictions about real fluids. And for the model to be deterministic, you need there to be a unique solution. So we don't know whether smoothness can be lost in finite time, but we can still ask the question, are weak solutions unique? Because any continuation must be a weak solution. And then this question would really become relevant if strong solutions break down. We'll just ask, are weak solutions unique? And we can provide some answers to that question today. All right, I want to say something about the success of weak solutions in some instances, specifically for scalar conservation laws, and even more specifically for Berger's equation. So we know if you study Berger's equation with, say, some non-trivial compactly supported initial data, then smoothness will be lost in some finite time. As long as the solution has negative slope somewhere, you'll form a shock discontinuity. Solutions will become discontinuous after that time. And yet, in spite of these shock discontinuities, you can find a uniqueness class of entropy solutions. And this notion of entropy solution, I mean, many people have contributed to this picture, but entropy solution we typically attribute to Kruskov. This is a picture of Nečas on the left, on the right, Kruskov. So I was fortunate to find this picture of them together on the memorial site. So in this case, the weak solutions are working. There's still uniqueness beyond the loss of smoothness. Moreover, if you add viscosity back to the picture, then solutions of this viscous Berger's equation, they exist for all time and they're smooth and unique. And when you send epsilon to 0, the viscosity parameter, the viscous solutions, the viscously regularized solutions, they converge to the unique entropy solution. So this is a very good picture. I just want to mention an interesting fact, which is that if you use a different kind of regularization, if you use a dispersive regularization with this dx cubed term, this is a weakly dispersive version of the KdV equation. And solutions of this equation also do not lose smoothness in finite time. They're smooth for all times. But when you send epsilon to 0, they do not converge to the unique entropy solution. So something about the entropy solutions, remember, if you like, you can think of it as it remembers something about the viscous regularization. I just want to show that, but I think it's an interesting part of the picture. So here are some numerics from the 90s. And the PDE convention here is that the nonlinearity is minus u dxu rather than plus. So some of these functions will look negative when we normally think of them as positive. And for the inviscid problem with no viscosity, the shock would arise between these two frames. We're supposed to read from the left. Let's start at the bottom. This is the numerical simulation of viscous burgers. And it seems to almost have a jump discontinuity here, but everything's really smooth, actually. Now, here is the numerical solution of the K-to-V equation with small dispersion. This solution, after the shock, becomes highly oscillatory. And when you send epsilon to 0, it will weakly converge to this weak limit, which one can predict and understand using theory. Actually, there's a theory for this due to Lax and Livermore. But let's also just say by inspection, this profile looks different than this profile, and they are different. Okay, so even when weak solutions are unique, one has to be extremely careful with the right notion and the right selection procedure. So back to Navier-Stokes. Recently, there's been mounting evidence pointing towards non-uniqueness of Leray solutions. And in 1969, Olga Ladzinskaya constructed an example of non-uniqueness for Navier-Stokes. And it was in a Leray-Hopf type class, but there are a few caveats. The first caveat is that her examples are in a time-dependent domain. And as time goes to 0, the domain shrinks to a point, making it a very non-standard initial boundary value problem for a parabolic equation. And also the boundary conditions that she uses on the side are not the usual no-slip conditions. They're conditions for the stream function. So she writes here that, well, I'll read it. The example described here can provoke displeasure for only one reason. It has been constructed for boundary conditions of type 18, but not for adhesion conditions. The examples presented here are interesting to me in that they refute the entrenched opinion on the naturalness for non-stationary problems of physics and mechanics of the class of solutions which have finite energy norm. Meaning, well, you might think I have some natural conserved quantities, natural monotone quantities, and you might corresponding to certain energies or entropies, and you might think the class of solutions for which those are finite and energy and energy are going in the right directions, you might think that's the natural class. She's making the point that she believes that based on her examples, it's not. Now, in the past 10 years, we've seen progress organized essentially into two different programs. The first program is work of Geospheric and Guillot. And this program, which I'll review soon, it produced compelling numerical evidence of non-unique Leray solutions, but no proof. So I'll explain this in a few slides. On the other hand, there have been convex integration constructions. In fact, this has become a whole industry. And last year at the IIS, there was a whole special year just on convex integration. And well, the state of the art is people can construct non-unique weak solutions. For example, in this class, continuous time, h beta and x, beta very small. And they have finite kinetic energy, but they don't have energy inequality because the gradient of the velocity field is not in L2. So these are all really proven, but they're not Leray solutions. So something's missing from each of these pictures. And here's our main theorem. We prove that there's a one-parameter family of distinct suitable Leray-Hopf solutions to the Navier-Stokes equations that have identical body force, which belongs to L1 and L2, L1, L2, and identical initial velocity, which is 0. Now, in these examples, since the initial velocity is 0, the body force clearly is playing a privileged role, an important role. But on the other hand, these solutions have some very nice properties. After the initial time, they're all smooth, the ones that we find. Any lack of smoothness that they have is only at the space-time origin. Also, the force, it's actually much better than L1, L2. It's really L1 time, L3 minus in X. And one way to think of this is that if we were to make the force any better, then all the solutions would have to be unique. This is really, we really capture a borderline case. I'll say more in a few slides, but this is the main theorem. We have some improvements. We can do this in bounded domains, for example, or in a periodic domain, but I won't cover that today. Okay. It's too bad that probably we can't take questions, but yeah, thanks for bearing with me. So I want to talk a little bit about self-similarity. In fact, I'm first going to talk about the possibility of self-similar singularity formation. This is not the main content of the talk. And what I'm talking about today, in a way, doesn't really have to do with singularity formation. I wouldn't say that it moves us closer to answering the Millennium problem. But this is related, this idea. Already in Laray's 1934 paper, he proposed a certain ansatz of backward self-similar singularity formation. What this refers to solutions which live for all negative times, ancient solutions, if you like, which are invariant under the scaling transformation, which I've written here. Now, these solutions necessarily have to satisfy a certain ansatz. You can write them in terms of what they're doing at time -1. So remember, they live for all negative times. Because if you know what they're doing at time -1, then by the scaling transformation, you know what they're doing for all times. So they necessarily are of the form u of xt is 1 over root minus t, remember times negative, so this is a positive number. And then they're written in terms of capital U. Capital U is a function of xi, which is x over root minus t. So xi we think of as a dimensionless spatial variable. And this, up to a time translation and some time rescaling, is really the ansatz written on the board here from Nečas's talk, apparently in the Heidelberg seminar. So you can try to understand whether this occurs. You can write down the P/E for what we call similarity profile. This is really the solution at time -1. Here's the P/E. And if you carefully analyze this P/E, then you can find in a famous work of Nečas, Růžička, and Šverák that if U, capital U, is in L3, which is a natural critical space to put the velocity field, then actually it has to be 0. So this essentially says if the similarity profile is in L3, then actually there's no self-similar blow. This is an extremely important theorem, which answers a question open since the 1934. So this was in 1996 at Acta Mathematica. And somehow, actually, the even better class, in some ways, the right class to consider is that capital U is like 1 over x, or 1 over xi in the new variables. So remember, this 1 over x really plays a privileged role in the theory, in the theory, because it's borderline. So this was answered by Vladimir's first student, Taiping Tsai. So now we know Laray's self-similar singularities actually don't exist under very general conditions, actually. All right, back to the content of the talk. So we're going to talk about forward self-similar solutions. These are solutions which are defined for all forward times. They're not ancient solutions. They start at time 0, and they live for all forward times, and they're invariant under the scaling symmetry. So you write them with a similar ansatz, except that I get to take out the minus signs under the square root. 1 over root t, capital U, which is a function of xi. Xi is x over root t. Now here are the equations for the similarity profile, and they're the same up to this minus sign, which actually plays a big role. And for these solutions, you can try to understand the following. You can try to look for these solutions when you prescribe self-similar initial data. That just means the data should be -1 homogeneous. It should be like 1 over x. and it should be divergence free. So when you solve the Cauchy problem with this self-similar initial data, this turns out this becomes an elliptic equation, like a steady elliptic equation for capital U, which is the profile at time 1, and the initial data enters through a boundary data at infinity. Capital U minus U naught should be little o of 1 over c. So this is the problem. And okay, I'm about to show you some pretty pictures, but first we're going to try to understand a little bit of try to understand the non-uniqueness scenario that John Sverak proposed. Okay, so I want to fix some self-similar initial data, meaning -1 homogeneous, and 0 body force. And let's call this data A naught, and we're going to grow the size of the data. You multiply it by sigma, like from the beginning of the talk, size parameter sigma. And our initial data you take to be sigma A naught. And when sigma is 0, you can certainly solve Navier-Stokes. Solution will be 0. What you do is you start growing the sigma parameter. And when sigma becomes large, the solution leaves the perturbative regime. On the other hand, you can still find self-similar solutions corresponding to this self-similar initial data. As you change the sigma parameter, this basically maps out, if you like, a curve in a function space. And you can ask this question: is there more than one self-similar solution for a given self-similar initial data? You basically ask, as I raise this sigma parameter, can there be some kind of bifurcation? Now, what John Sverak looked at is they looked at the possibility of this bifurcation. They said, suppose it does occur. Let's just say, suppose there's a saddle node bifurcation. And that would mean that there are 2 different self-similar solutions with the same self-similar initial data. That's already non-uniqueness right there. However, those self-similar solutions have infinite energy. They decay like 1 over x. And that's not square integrable in 3 dimensions. However, if you carefully truncate these solutions at large distances, then you can actually get 2 different self-similar solutions, or sorry, 2 different Leray solutions. They'll just be locally self-similar, and they'll have identical compactly supported initial data. So this is the scenario. And it's hard to prove anything about this scenario to really prove that it occurs. What you would have to do is you would have to write down the linearized operator around the similarity profiles, and you would have to study its spectrum, and it's very difficult. But you can put it on the computer. So you put it on the computer, and you choose a particular initial data that has a reflection symmetry across the z equals 0 plane. So it has a symmetry. And you also choose data which is axisymmetric with swirl. And that makes the computation 2-dimensional. It makes it feasible to run on a computer in a reasonable amount of time. And what we're looking at in this figure is we're looking at the swirl component, the E theta component of the solution at time 1. We're looking at the similarity profile, its E theta component. After a certain bifurcation occurred, the kind of bifurcation is called a supercritical pitchfork bifurcation, and it breaks that reflection symmetry that we put on the initial data. This here is one of the symmetric solutions. This here is one of the non-symmetric solutions. As you can see, this kind of swirls up, if you like. And there's another non-symmetric solution which swirls down. So there are 3 self-similar solutions with the same self-similar initial data, at least according to these numerical predictions, these predictions which are in which all the computations are only in the class of smooth functions. Now, okay, here, this is a plot of some of the low-lying eigenvalues of the linearized operator. We can see that when sigma is about 292, one of the eigenvalues does become unstable. Its real part changes sign. So this is the numerical picture. I want to say something about these, about why do we expect these kind of bifurcations? Now, we expect them partially because they arise in nature. Let's look at the linearized operator again, or let's look at the similarity equations again. If you ignore these terms, these first two terms, which come from the change of variables, what you're left with is just stationary Navier-Stokes. And these kind of bifurcations, they really do happen all the time for stationary Navier-Stokes. What we're looking at here are numerics from flow around a cylinder. So you should, no. You should imagine that you're looking at, a cylinder top down, and there's some cross flow coming from the side, coming from this side. And you can form, you can form dimensionless quantity, Reynolds number, based from the scenario, but you should just think that you're increasing the flow speed from the side. And when the flow speed is very small, you'll see a time-independent solution, these stationary solutions. And when you increase the flow speed enough, you see time-periodic solutions instead, because what's occurred is a Hopf bifurcation to what we call vortex shedding. Now, by the way, to the best of my knowledge, this is not yet a theorem. It's an experimental fact that there's a Hopf bifurcation, but it's not yet a theorem, to the best of my knowledge. Now, one of the reasons why it's not a theorem is the same reason why we can't yet prove this geospheric picture. It's because the solutions that you're trying to understand are not really explicit. You can prove they're there, but you can't really write them down and then linearize the equations around them and actually try to calculate eigenvalues. It's they're not explicit enough. It's somehow too difficult. I'm going to tell you a little bit about how you can make the solutions explicit and do the computation and come up with an answer. First, I want to interpret those self-similar solutions as steady states of a certain evolutionary PDE. So this was the equation that we had a couple slides ago. With that, then I've just added d tau u. This is now an equation for the similarity profile, and it has a time derivative in it. And it turns out this is actually just Navier-Stokes in a new set of variables. They're called self-similarity variables. And the new variables are c is x over root t, and tau is log time, logarithmic time. So importantly, tau goes to minus infinity when little t goes to 0. This will be important. So then you can rewrite any velocity field as 1 over root t of capital U. Capital U is a function of the new variables. Capital U lives for all negative tau. It's a function of tau. It lives for all negative tau. And the important point is that actually this change of variables, it encodes all the low regularity in this problem. If capital U is very nice, it's smooth and decaying, then little u in the physical variables automatically belongs to critical spaces. It automatically lives on the borderline of the well-posedness theory. And so now I can study a smooth dynamical problem for capital U in this PDE. And I can study something about long time behavior of capital U. And that will correspond to something about lowercase u in low regularity. Okay, here's what we're going to do. I told you that the geospheric and geode picture was difficult to make rigorous because the solutions are not explicit. You can make the solutions explicit if you allow yourself the flexibility of a body force. In this way, you actually get to choose your solution because from a certain perspective, you can take any smooth function and plug it into the equation and it'll generate a force. And that force will just be whatever you get when you evaluate dtu plus u grad u minus Laplace u. It'll just be whatever pops out when you plug in a smooth function. Now, this might sound a little strange. Actually, people who do computations know that this is a method for benchmarking or verifying your numerics. This is called method of manufactured solutions or method of engineered solutions. We're going to use the same idea to study the non-uniqueness problem, but now we get to choose our self-similar solution. So the new setup is this. I want to find a similarity profile. I'm going to call it capital U bar. And the bar stands for background because I'm going to linearize around this solution, and this solution kind of becomes the background. So I need to find a capital U bar. We're going to find it to be smooth and compactly supported, also divergence free. Most importantly, we want to find it so that the linearized operator, I'm calling it LSS, the linearized operator should have an unstable eigenvalue. Once you have an unstable eigenvalue, there's a way to get non-uniqueness, which is to construct the unstable manifold of capital U bar. Now, let me just say a bit about unstable manifold. Let's just talk about ODEs for a second. Let's think about the ODE. X dot is f of x. F is the nonlinearity and also the force terms. Let's say there's some equilibrium, f of x naught equals 0. So x naught is the equilibrium. Then you can linearize around the equilibrium. The linearized equation is y dot is the derivative of f. This is a matrix applied to y. If I want to study the behavior near the equilibrium, then I can write down the spectrum of the matrix. Here it is. And I look at unstable eigenvalues. Those are the ones in the right half plane. And if you look at if you look at the subspace corresponding to those unstable eigenvalues, you know that if you run the linearized equations starting in that subspace, well, they're unstable. So you have growth forward in time, but backward in time, you have decay. They're unstable forward in time. They're stable backward in time. That's just the linearized picture. Oops, sorry. That's just the linearized picture. Wow, I really skipped a lot of slides there. That's just the linearized picture. But there are really nonlinear solutions to the ODE which track these dynamics. That means backward in time, they converge to the equilibrium. It's not difficult to generalize this to semilinear PDEs. Okay, so this unstable manifold picture, you can think of it as non-uniqueness backward in time, but the way we're using it is not in time. We're using it in logarithmic time. We're using it in tau. So what you have are you have a family of solutions. Backward in tau, they converge exponentially to capital U bar. That means they have the same initial data as capital U bar. However, these solutions are really different. So all these trajectories on the unstable manifold, they are the non-unique solutions. One of them is self-similar, and the other ones are not self-similar. So this is one of the pictures that you can use to generate non-uniqueness. It's about instability in a new set of variables. Okay. So now I'm going to say a little bit about how do I find my unstable self-similar solution. That's my new mandate. I need to find an unstable self-similar solution of Navier-Stokes. And it would be a lot easier if I could just throw away some terms. It'd be a lot easier if I could find an unstable self-similar solution, or sorry, just an unstable steady state of 3D Euler. And you can actually reduce the problem to this question about unstable steady states of 3D Euler. What you're going to do is, if you have a background U bar, you can increase its size, because remember, we get to just choose our background. We have this freedom. So you can multiply it by a parameter beta and make it very large. And when you do that, the terms which come from 3D Euler, they dominate compared to these terms, including the viscous term, and then these extra terms which come from the change of variables. These terms, they don't have a beta, so they look like order 1. These terms look like order beta, so they dominate. And this is just a heuristic, but you can actually prove something which reduces the problem to finding unstable steady states of 3D Euler. But importantly, these unstable steady states need to be smooth. They need to decay at spatial infinity, and their linearized operator should have an unstable eigenvalue. And with all these qualifications, all these qualifiers, actually, especially if you just look in PDE literature, no steady state was known for 3D Euler satisfying these qualifiers. So we need to construct our own. We know a lot more about unstable steady states of 2D Euler, so let's just talk about that. They're explicit steady states known as vortices. These are just, well, any function whose vorticity is radial, depends only on R, that'll be a steady solution of 2D Euler, and you can study these. So if you linearize 2D Euler around a vortex, then, and you try to understand linearized operator, you'll be in good company, because this is what Rayleigh did in, I believe, 1880. Or anyways, the late 1800s. Now, so Rayleigh had a condition for stability. We're trying to look for instability. And recently, actually, in 2018, Misha Vishik proved that there is a smooth, unstable vortex. You can also truncate this vortex. You can get it to be compactly supported and keep it unstable. And this is something that we note in our work. The idea for this unstable self-similar solution, or sorry, this unstable vortex, in some ways is quite old. It goes back to 1930s with work of Tolmian. Tolmian was a student of Prandtl, but it was only rigorously proved in 2018. So now you have an unstable vortex. I just want to say that Vishik has his own reasons for proving that there's an unstable vortex. He had his own non-uniqueness problem in mind for 2D Euler. Now, because 2D Euler, if you start with bounded vorticity, then you can find weak solutions which have bounded vorticity. And that's actually a uniqueness class. We call it, you might call it Udovich class. On the other hand, you can also find weak solutions with vorticity, which is just an LP. And you might ask the same question, okay, are those unique? And Vishik was able to show that they're not unique. But his work was difficult to understand. We felt that it wasn't well understood by the community. And in fall of 2020, 7 of us started reading Vishik's work and trying to piece it together. And very early on, we saw analogies with the work of Gian Schwerak. And in the end, we wrote these lecture notes, which give an exposition of Vishik's work. So they're on the archive. They'll be published as a book. And we give Vishik all due credit. His name is in the title of the notes, and we're really following his proof. But we've written it in a way which we think will be helpful for the broader PDE community. Okay, this was a long detour on 2D Euler. Let's go back to 3D Euler. I'm trying to find an unstable steady state, which should be smooth, decay at infinity, and have an unstable eigenvalue. And our object is going to be an unstable vortex ring. Of course, vortex rings are real objects. Here's this vortex ring of steam, which has been shot out by the volcano Mount Etna in Italy. Well, it's this small ring here. I didn't make it bigger because I wanted to keep the mountain in the picture. Mathematically, the vortex ring that we're looking for is going to be axisymmetric without swirl. And you can write it in axisymmetric variables. So down here, we have it schematically. It's a function of r and z. And the vorticity, and actually, in our case, also the velocity, will be supported in a core. And this core is going to be distance little l from the origin. Little l is going to be very large. So these vortex rings, you think of them as their core is like size 1, but they live very far away from the origin, and then they're wrapped around the z-axis, really. And we call them vortex rings of small aspect ratio. And they've actually been studied for a long time. They were studied by Kelvin and Helmholtz already. But they're the right object for the construction that we wanted. The reason that they're the right object is because we have an unstable steady state in 2D Euler. And 2D Euler it actually lives perturbatively in 3D Euler axisymmetric no swirl. It lives there at large distances. So you can write down 3D axisymmetric Euler no swirl as an equation for the vorticity, the E theta component of vorticity. And if you ignore all the terms with 1 over r, you just get 2D Euler. It's 2D Euler where r is like x and z is like y. That's how it fits in the picture. And so you have this idea, and then the way forward starts to become clear. I'm going to take Vishik's 2D vortex. It's going to serve as the core of my 3D vortex ring. And I'm going to take the aspect ratio very small, which is the same thing as taking this little l very large. And I'm going to try to show perturbatively that the 2D instability is inherited in 3D. So this is what you do. You really take this unstable vortex and you put it as the core of your vortex ring. And when you do that, it's no longer divergence free, but you can make a small correction to keep it divergence free. It's not an issue. And it's also useful to center your variables on the core of the vortex. And so when you do that, you're going to let R extend all the way back here to minus L. And when you take L to infinity, this will fill out the whole 2D plane, and the operators should formally converge to 2D Euler. So what you do next is you write down the linearization around the 3D vortex ring, and you write down the linearization around the 2D vortex. I know that this linearized operator is unstable. I'm trying to show that this linearized operator is unstable. And I don't really expect you to read all the terms, but let me just say something about the 2D operator. The 2D operator has two terms. It is the term where the vortex, the background, which I'm calling U tilde here, there's a term where that background advects the perturbation U tilde dot grad. And this term is anti-symmetric because U tilde is divergence free. So its spectrum lives only on the imaginary axis. And there's a second term, which is the term where the perturbation advects the background, or at least tries to. So that's U dot grad omega tilde. And because you apply the Bios of R law, you gain some regularity because omega tilde is compactly supported. I mean, this term is compact. So we know it cannot change the essential spectrum. It can create some unstable eigenvalues. And in this case, it does. And we're trying to understand what happens to those unstable eigenvalues when I put them in the 3D picture. So you do a spectral perturbation argument, and this is where all the estimates are hiding, right? This is a PDE paper. There's estimates somewhere. They're hiding in the proof of this proposition. What you do is I take an eigenvalue of the 2D operator, and I look at the spectral projection onto that part of the complex plane, which I define by integrating the resolvent. And if this spectral projection is non-trivial, I know that there's an eigenvalue inside this contour. So what I'm trying to show is that the spectral projection for the vortex ring is going to be non-trivial. And I can do that if I show that the projections converge. I'm trying to show the projections for the vortex ring converge to the projections for the 2D vortex. And how do you do that? You need to show the resolvents converge, resolvents of these linearized operators. So now I'm going to compare the two linearized operators. And okay, now you're doing estimates. Now you're really doing PDEs. So all that is hidden inside this picture, this spectral perturbation argument. All right, let me briefly conclude. Okay, actually, let me say, once you do this picture, then I still need to add on the viscosity terms using more spectral perturbation theory. I still need to prove the existence of the unstable manifold, all these things. But those, they either follow this scheme or they're more standard. So there's more work here, but this is somehow the core. All right, the conclusion. So there are a few questions. People often ask, is it possible to remove the force? And I'll say, I don't know how to remove the force using my methods. On the other hand, people have talked about trying to do a computer-assisted proof using the numerics of Schwerak and Guillaume. I think that would be very interesting. I'm not currently working on it. People in the community have been talking about this idea for a while. And I think it would be very interesting because nothing like that has been done before. What I'm somehow more interested in is getting closer to the more perfect picture. Something like first blow up and then non-uniqueness, or getting non-uniqueness when you take some kind of singular limit. Like, for example, if you take inviscid limit from Navier-Stokes to Euler. These are two different kinds of scenarios that you can look for. And in terms of non-uniqueness after finite time blow up, at the moment, you can't really study that directly for Navier-Stokes because you can't prove Navier-Stokes blows up or doesn't. But you can study it for other equations, and it has been studied. There are quite a few examples. So there's examples for focusing NLS, examples in harmonic map heat flow. Vladimir Šverák has his own examples, which are currently at the numerical level for complex Ginsburg-Landau. And if you're interested in this, he gave a beautiful talk called Lessons from CGL, which you can find on YouTube. It's an online lecture. Unfortunately, the paper is still not out, but we await it with bated breath. And I'm very interested in this direction. One can try to work on proving more examples, but also even in the existing examples, you want to study whether or not there's some kind of selection principle. And this goes back to the Burger slide that we saw. Burgers has a uniqueness class. You can get that class using viscous regularization. If you use the dispersive regularization, you get something else. So the ideal picture is more like if you have a physical problem where non-uniqueness is somehow an issue, you should try to work with a model which preferably incorporates more physics and which does not blow up. And then when you take some kind of limit, you hope to recover really the right solution. You hope that there's a selection principle, but actually it's starting to look like there are important instances where there is not really a selection principle. And this is actually being partially made clear by numerical computations being done by physicists. There's an example where they study non-uniqueness when you take the inviscid limit to a vortex sheet. A vortex sheet is a very singular object, so there's not well posedness near it. And when you take this limit, you can get non-unique solutions if you set things up correctly. So this problem, it's somehow not just in a way, it's not just mathematicians playing around. There are real questions here about what would the implications be for if you have deterministic systems or systems which are supposedly deterministic, which you want to predict future motion of the fluid, say, and which do have kind of non-uniqueness due to extreme instability. So I don't have time to show the numerics at the moment, but in any case, so this is a very interesting prospect, which I think people in PDE land are just starting to understand. Okay, thanks very much.
Thank you very much for your very nice talk. I hope you can hear me now.
I can hear you now.
Okay, good. So we have time for some questions. So maybe first here in the audience in Prague, are there some questions to the talk? So maybe I will have one question. So what do you think? You expect that if you start with regular data, you expect that there will be a blow up and then some kind of possible non-uniqueness later on, whatever, or you expect that if you start with very regular data, say regular right-hand side, there is no chance for the blow up? And
that's a good question. So currently, I don't know. And indeed, nobody knows. But I think there are some things that people are kind of agreeing on, which is that if there is blow up, then it should be unstable, which is why we never see it in numerical simulations. And if you work in the self-similarity business, there are ways to connect possible Euler blowups to Navier-Stokes blowups. In principle, one could have a 3D Euler blowup, which is unstable and self-similar, and in such a way that it actually also lives in the Navier-Stokes picture, that when you go to self-similar variables, the viscosity looks negligible. So there's these kind of scenarios, and also even though self-similar exactly, the Laray's self-similar blow-up ansatz, we know that there shouldn't be any blow-ups in that class. There are other classes like discretely self-similar blow-up or self-similar blow-up with rotation, which people have proposed, which have not been ruled out. And so those are currently the next kind of simplest simplest coherent blow-ups that people don't understand. So I don't know. The answer is I don't know, and I have no leanings either way. But our understanding of it is improving, and I think with the use of more computers, we might see an answer within 20 years, say.
Thank you. Some other questions? Maybe some online questions?
I have a question.
Great.
Yeah, thank you for the extremely nice lecture. Really fantastic result and very nice presentation.
Thanks.
Yeah, I mean, I was actually also reading your paper. It's also written very nicely, but I was not reading Růžička's work or your lecture notes on it. So maybe you could say something about this force of Růžička on the right-hand side. Is it somehow related to this numeric pictures which you had, like this vortex shedding after the obstacle, or is there any relation?
It's so it's not related to those pictures. The force of Růžička is in some way similar to ours. He is going to choose a self-similar solution, and it's not exactly going to solve 2D Euler, but it solves it with a force. And then he's going to go to the right self-similar variables for Euler. He's going to study the linearized operators. In the end, he's going to show that there's an unstable eigenvalue and construct unstable manifold. But in the paper, he won't write those words. But all of that's there. And when I talked to him, he said, "Oh yeah, of course you can phrase it like unstable manifold." So he knows. Yeah, he knew, but somehow it's helpful for the rest of us to make this analogy. And again, this idea is already in Jasperak, and some of these ideas also play a role in singularity formation. So they're kind of hiding around. But anyways, that's how the force arises. Yeah. Thanks.
Thank you.
Yeah. Other questions?
May I ask a question? Thank you very much. I'm highly interested also in your last remark, because you said it's not just interesting for Navier-Stokes, but also, for instance, for harmonic maps.
Yes.
Although closely related are the chemotaxis equations, which we have.
Yes.
And we also have used for the finite, showing that there's a real proof for explosion in finite time if you use Berger's equation. But I would be astonished. We would have to formulate the equations beyond, if you prolong it against such a squeezing off these fruiting bodies, that we would lose uniqueness. That's why I'm a little bit astonished. I would like to have a formulation of this continuation of the equations in order to guarantee that singularities can appear, but the continuation should lead to unique solutions too. Because otherwise we would have a problem with the model. It could happen in harmonics, but the harmonics are very close to, or chemotaxis equation are very close to harmonics. I have been always thinking also in the estimates how many singularities can appear in the chemotaxis. Why do you think it's losing the uniqueness?
Well, so in harmonic maps, so there are a couple scenarios. Caron has some scenarios, but the scenario I'm thinking about is so it does have a feature which is not shared by chemotaxis systems. So in critical harmonic maps, let's say from the torus into S2, so 2D to 2D, then when you have the bubbling blow up, really at the singular time, that bubble disappears and the energy drops. And the way that, at least in this scenario that I'm talking about, the way they get the non-uniqueness is to add a bubble back in, which expands after the blow up time. So this is a very weird scenario. It's somehow not, it's not dissipative somehow.
For harmonic maps, I have an image where this would not coming automatically. If you would have to add something, but then I don't know how you formulate it.
Right. No, so that's and in fact, Struve if Michael Struve has a uniqueness class, which makes this very weird. So this class probably arises. I mean, this is a
Also,
question
Mariano
that,
Chaquinda had formulations also where you have squeezing off. It's mainly losing the fact that we have a wrong representation of this time evolution. And then it comes and you squeeze always off uniquely determined spheres.
yeah, I think this is this scenario is a little bit weird, but I think the question here is if you regularize the equation in a certain way and pass to a limit, is it possible to obtain this? I think that's the question for this. This is somehow a very unnatural, yeah, I have some plans to study this a little farther. So, yeah.
Okay.
No, also for chemotaxis, as you said, yeah, I agree. Very interesting.
Okay, some further questions? So, since there are no more questions, so Dallas, thank you very much for your very nice talk.
Thanks.
And I hope to see you in Prague maybe next year.
I hope to be in Prague maybe next year.
Okay, so we will have now a half-an-hour break and we will resume at 5:10 by the lecture of Michal Růžička. Bye, Dallas.
Bye-bye.
Michal Růžička studied here in Prague, did his PhD under the supervision of Professor Nečas. Then after several postdoc positions, for example, in Bonn, in Ferrara, in Pittsburgh, I think, he ended up now in the University of Freiburg, where he's the professor, and he will speak on existence proofs for pseudomonotone parabolic problems. Please.
Thank you very much. It's a big pleasure for me to have the possibility to speak here today because Nečas was my supervisor and I spent here a lot of time and have a lot of nice memories. So this lecture is somehow dedicated to Nečas, and the first time I spoke here in the seminar was almost, let's say, 35 years ago. I don't remember much of this lecture, as I learned other people do remember something about it. But what I do remember a lot is Nečas, who was in this time, as Milan already said, my supervisor. And especially in the time, late 80s, beginning of 90s, Nečas was spending half a year in DeKalb in the US and half a year in Prague. And somehow when his return to Prague was due, the atmosphere in the institute changed. Because everybody was knowing he comes back full of enthusiasm, full of new ideas, full of new problems. And he shared this with his group. And one year he came back and he got interested in this kind of equations, which we call P Navier-Stokes equation, because that's a version of the equation you have seen before, or a generalization, because if P is equal to 2, this is a classical Navier-Stokes equation. And Yeah. Okay, so let me tell something about the story of this equation. Now the pointer does not work anymore. Nope. No, ta technika. No, to je tak nějak blbě. Jinak nevím, na který z těch. Je to úplně zmrznutý. Je to úplně zmrznutý. To jde. Jo, už to zase funguje. So, the first contribution in this direction was by Leray and Hopf. We learned already in the previous lecture about it, that this for the special case p equal to 2. The first result really related to the p Navier-Stokes equation is due to Růžička and Lyon in the late 60s, and they were able to show by monotone and compactness results to get existence for this number, and it is in 3 dimensions 11/5. And that, in fact, was also one of the motivations of Nečas to study this and to improve these results, because p equal to 2 is Navier-Stokes. This number is larger than Navier-Stokes, so there's a gap, and he didn't like the gaps. In fact, the next contribution is already by him and his collaborators. So there are many. I don't want to name all of them. And he was able to improve this number to, in 3 dimensions, 9/5, which is clearly smaller than 2. So Navier-Stokes is included in this contribution. And what his idea was, he tested essentially with the Laplace operator, and he was not able to get the full information, so no second derivatives, but some broken derivatives of the first gradient, and that is enough for compactness. But that's not the end of the story. This equation were interested by men, there was a lot of interest about these equations, and Frese, Malik, and Steinhauer in the periodic setting, and Jörg Wolf in the Dirichlet case were able to improve that number even a little bit more. And now the number is 8/5. And the idea there is to use an L-infinity truncation, which essentially means you allow test functions from the space L-infinity, but you have to modify somehow your solution that it belongs to that space. And you can do even a little bit better. This is due to Lars Diening, Jörg Wolf, and myself. So that number is now 6/5. And that is by now standard Lipschitz truncation method. And in fact, this in a sense is the best result you can hope for if you want to understand the convective term as an integrable function. But if you allow to interpret that a little bit more general, then Eduard Feyreise and Anna Arbitiello in 2020 showed that there exists dissipative solution, which is a weaker notion of solution for p larger than 1 over p larger than 1. So that's the end of the story, because I think both from the physical point of view and from the mathematical point of view, lower numbers will be really complicated. And in fact, why one was looking for low numbers, because not only from the mathematical beauty to include p equal to 2 and to have better results, but also from the physical point of view, low numbers of p are more frequent in the applications. So my today's talk will be related to that, but more on the basics, because all these results, let's say starting from here, are using some kind of approximation procedure, and you want to get, without much effort, these solutions. And in fact, if you do it carefully, it takes usually quite some 4 or 5 pages to prove it, and before you even come to the heart of the matter, what you really want to do. So to avoid this, we started to look a little bit more in detail to the pseudomonotone operators in the unsteady setting. But let me start with the elliptic problem, because there the theory is very, very nice. So what we are doing, we are looking for a solution in a space V, which is a reflexible separable Banach space, and we want to solve a nonlinear equation. Okay, when is this possible? One possibility is the case of monotone operators, proved by Brawler and Minty in the 60s, and it says if we have a coercive monotone hemicontinuous operator, then it is surjective. This means that we can solve this equation for every right-hand side. That could be improved a little bit to the pseudomonotone case by Brézis in the late 60s, and essentially the assumptions are the same. You now need a pseudomonotone operator, which is coercive and bounded, and again, you can solve this equation for every right-hand side. So monotone is very easy. This is just a sign condition, so it's essentially an increasing graph. Pseudomonotonicity is a little bit more complicated, so let me write down once the definition. For those who don't remember, including myself, I always forget this, but essentially what we have a weak convergence in our space. We have a lim sub condition with a sign on the right-hand side, and if this is fulfilled, we get a lim-inf condition with the operator on the other side. And essentially, this is a continuity principle, which also reminds compensated compactness and gamma convergence. And if you have the second condition, you can easily identify that the limit of a weakly converging sequence up, and you apply the operator to it, that you can pass there with n to infinity. Okay, so that's the elliptic case. There the situation is almost perfect. Let us see what is a typical application. So a pseudomonotone operator, essentially in most cases, is the sum of a monotone operator, this is hemicontinuous, and a compact perturbation. So that is a structure, and typical examples are this perturbation with function g of u of a P-Laplace equation, and the P-Laplace operator, of course, is monotone and it's even continuous. So that's a nice guy, and to handle the compact term, you want to use in the steady case the compact embedding of the Sobolev space into a beta LP space. And if this is smaller than the critical best exponent, then we have a compact embedding and the operator is compact. And of course, you need for that a little bit of growth conditions, and to ensure coercivity, you need that condition. But you can apply it. And the other example, which is more to the applicational side, this is a P Navier-Stokes equation in the steady setting. There, the new ingredients is that you have now divergence free vector fields. You have that number, and then you can show that the convective term, even if it contains a derivative, is a compact operator. So that's a picture in the steady case. So let's look now to the unsteady case. So there the problem is a little bit more problematic. You need a little bit more of structure. And the first thing you need is a Gelfand triple. The Gelfand triple is a separable reflexive Banach space, which embeds into a Hilbert space, which can be identified with its dual. And therefore, you have this chain here, Banach space, Hilbert space, identified, and you can embed it into the dual of the first space. You need that. And then you look at the same equation, you just add the time derivative. So we are now looking for solutions in the space X, which is the Bochner space with values in V, and we want to solve that equation here. And so again, if you look into the literature, you see there's a very nice result by Browder and Brézis or Showalter later, And this theorem says if you have a pseudomonotone operator, which is bounded and coercive in this sense, then we have for every right-hand side and every initial condition a solution even in a little bit nicer space, namely that the time derivative is in the dual of the space X. Okay, so to understand this result, one can take the following point of view. I started with my steady problem, so I take my steady operator and insert it into the unsteady situation. So this is an induced operator, which is nothing else than you just plug in the time instant of your unsteady possible solution. So now let's look at the structure. What happens in this simple situation? Then if the steady operator is monotone, just inserting then the induced operator, of course, is also monotone because it's just a sign condition. On the other hand, if the operator, the steady one, was pseudomonotone, which is easy to verify because there we have these nice compact embeddings. In general, the induced operator is not pseudomonotone. What is the reason for that? Because we start with a weakly converging sequence, but that is in the Bochner space, and we want to use that the B is pseudomonotone, so we have to break it down to the time slices. But of course, this in general does not imply that, and therefore we cannot make use of the fact that the steady operator is pseudomonotone, which has a consequence that essentially this very nice general theorem about pseudomonotone operators is only applicable in the monotone case. And that is not really satisfactory. And therefore, we looked on alternatives. And in fact, one of the alternatives goes back to Lyon, and which was exactly the proof which I mentioned already in the beginning in 1969 for the P Navier-Stokes equation. And let's have a look what's happening there. So what you need there, okay, the other paper is by Hirano. Both looked at concrete problems, but we were interested in giving a general abstract theorem. We have Banach spaces, not concrete Sobolev spaces, and show an existence result. So in order to do so, you need assumptions on the spaces and on the operator. For the spaces, we need, again, the Gelfand triple, but moreover, we need a small space Z, which is densely embedded, and we need projections in the Hilbert space, which of course are continuous and bounded, but we need that they are all bounded with the same constant and not only in the space H, but also in Z. And that is a technical condition, which we will see is easily to be satisfied, but it's a little bit of effort. So what do we need on the operator? We have again our steady operator. It has to be pseudomonotone. It has to be coercive if we have a P structure. So we have this P here. And it needs a certain growth condition in order to get a priori estimates. And if that is satisfied, we get the following abstract result, motivated essentially mimicking the ideas developed by Lyon and Hirano. This was done together with my student Erik Bäumle in 2017. So if the spaces satisfy these two conditions and the operator the other three, then we get again the same result as in the abstract Brouwer theory. We get existence for all right-hand side and initial conditions. The idea is, of course, we use the coercivity to get information and a priori estimates. We use the projections to get control about the time derivative, in fact, not of the final solution, but of the approximating sequence. And then the trick is to use the Aubin-Lyon's lemma, which shows exactly in this situation that we have compactness. And the point here is that the time derivative is controlled not on the dual of the space X, but in this much larger space. And in general, you cannot do much better. And so let's see when it is applicable. We have these two typical applications. The first was the perturbation of the P now heat equation. And there it is easy to find the space Z. So you just take the Hilbert structure and you take as much derivatives as you have dimension, and you can easily do so. You need growth condition. Now this upper bound is a little bit more restrictive because that's usually the case. You have upper bounds or growth conditions for steady case, and the structure is the same. But if you want to treat the unsteady situation, you need more restrictive upper bounds. And then it works. And also for the P Navier-Stokes equation, it works. Again, you have to take this space and you get exactly this number I was mentioning before, and that proof in this concrete situation is due to Lyon and Růžička. Okay, so that is nice. Let me go back. That is nice, but there is too much you have to check, because essentially this technical conditions about the space that it's just really it's technical. It's just that you can identify a limit. Otherwise you don't need that anymore. And we were looking around if there are other results proving similar things, and we found a nice paper by Landes and Mustonen from '87, again treating Navier-Stokes equation and giving an alternative idea for the Aubin-Lyons compactness result. So his result is the following. You need a sequence in L infinity L1, which is weakly converging in a Bochner-Sobolev space. And this new condition is that at each time slice, or almost each time slice, your sequence is converging weakly in L1. And then you already can conclude that your sequence is compact in, again, the right spaces. So that is like a version of a compactness result without having any condition on the time derivative. Okay, so that is applicable to both situations. You can check that easily. The drawback is the proof of this very nice result is done by mollifiers. So you take mollifiers in space and time, and you make a certain exchange with you change your point of view, one from the time point of view, one from the space point of view. And of course, if you have a general Banach space, I don't know of any mollifier method in a general situation, and all my friends from function spaces, nobody could help me. So that is not nice. But nevertheless, we succeeded together with my student Alex Kaltenbach very recently to find a way out of this. So the point is the following. In the pseudomonotone operators, this is just you take the elliptic theory and you transfer to the unsteady case, let's say time slice wise. And you don't use the additional term which is there, namely the time derivative. You just simply forget it. And therefore also this result is weak, that it only applies to monotone operators and not to pseudomonotone operators. So the way out is you modify your notion of pseudomonotonicity. We called it Bochner pseudomonotonicity. And the new ingredients are two. First of all, you take the weakly convergent sequence also in the space L infinity H, which is exactly the a priori information you get from the time derivative. So you should not forget it, but you take it into account. This condition is the same. And then we take exactly the Landes-Mustonen analog. We require that the sequence converges on almost all time slices weakly in H. And if this is the case, we can conclude that we have this condition here satisfies, which then together with Min-Dietrich allows us to identify the limit. So that's a new notion. It is stronger than pseudomonotonicity because we require more on the sequence, but it turns out it will be better fitted to applications. So let's have a look. So we take again our operator, which now satisfies only the conditions of the operator, no conditions of the spaces. Then if the steady operator satisfies these conditions, one can easily show that the induced operator is Bochner pseudomonotone. So that makes also this notion very easily applicable, because you just have to check on the steady operator growth and coercivity and continuity, and then it immediately goes over to the unsteady situation. We can therefore show, if we have this Bochner pseudomonotone operator, we get a solution of our problem. And the basic ideas are, again, the coercivity of the operator and the time derivative give us a priori estimate now both in the information from the operator and the information from the time derivative. And now there is this new condition here. So where do we get that? Again, it comes directly from the equation. We don't have to assume anything new. We don't have to do more. It is just already in the equation. We just have to see it. And therefore, we can show that the new condition is satisfied. And we can conclude that this new notion is now applicable not only to monochrome operators, but to pseudomonotone operators. So all the typical examples are included. In fact, in the moment, I don't want to go a little more in details of the proof, because I want to do it later. Because it turns out that this notion of Bochner pseudomonotonicity is very robust. It can be adapted and even be used to prove that numerical schemes converge. And so let's go a little bit in this direction. So because if we have this highly nonlinear equations and we can show, okay, there's an existence of solutions, then comes some engineer and says, okay, that's nice that you can show it, but I want to see it. And then you go to your friend from the computer department and he says, okay, I program something and you can see it. But then I would like to know, okay, does this what he did has to do anything what I gave him? And so therefore we have to prove something, but first we have to understand a fully discrete setting. So again, we have a Gelfand triple, we have a time interval, and we have Bochner spaces. And if we have this, we can always, because the space is separable, we can find finite dimensional subspaces which in the union are dense. And we are interested in initial condition and right-hand side from the general spaces. So also there we can assume this is in fact can also again be shown always that the initial conditions are a little bit nicer, but still converge, and the right-hand side also is a little bit nicer, but this is more or less technical. And then what we do, this was the spatial setup. So what we do in the timeline, we just cut the time interval into small pieces, which you can see here. And we replace the time derivative by its definition, which is a difference quotient. And this tau we call step size. And we hope that we can solve these equations. And if we have it, then we have discrete objects just on this times here, T1, T2, T3, but what we need, if we want to pass to the limit, we go back, we take either a piecewise constant interpolation of these points or a piecewise linear interpolation. In fact, both will be seen to be needed. So that is a discretization setup. And what can be done in this setup? So we are consider again the same problem. We look for the same equation. We look for a solution in the same space. But from the numerical point of view, we want to prove something that we have something which we can compute in the computer. So therefore, we take a fully discrete scheme. We just replace on all places the continuous solution by the discrete ones. And moreover, since we also discretize in time, we have really a fully discrete object. And we replace the time derivative by the difference quotient. So one can show easily by Brouwer's fixed point theorem that this is solvable. But for that, again, we need some assumptions. The assumptions are exactly the same as before. The operator, the steady operator, has to satisfy these three conditions. And then we can show that there exist discrete solutions of this equation PD. And we take the piecewise constant interpolant, and we are looking what happens with the limit. And the answer is that each weak accumulation point or of the sequence in this space, which comes from this is natural a priori estimate space, each weak accumulation point is a solution of our original problem, and it has the right regularity. Of course, if we have such a nonlinear problem, uniqueness is not guaranteed, so therefore we can have several accumulation points and we don't have uniqueness. Okay? So that is an very abstract setting, but it can be realized, of course, with a finite element setting in the typical example 1, which was a P heat equation plus a compact perturbation. And so you just take your domain, you make a triangulation, and on each triangulation you have a polynomial, which on the interfaces, of course, is still continuous. Therefore, it's called finite elements. Okay, so here probably I want to go a little bit of the details to show you also how this notion of Bochner pseudomonotonicity works. And in fact, we have a few additional complications due to the discrete setting. So we need a priori estimates. So it's energy methods is clear. We have to test by the solution. We do so, and we get this inequality here. This is a discrete inequality. So the assumptions, especially the assumption on the growth condition, was done in such a way that you can apply Grandvoir's lemma, or here is discrete version. You do so, namely the discrete Grandvoir's inequality that gives you that you have a boundedness, but this transfers to the piecewise constant interpolation and also to the piecewise linear interpolation. This is generated by these points. So we have these a priori estimates here. Okay? And if you have a priori estimates, the spaces are nice. We can go to sequences or subsequences weakly converge. And here you see already the first point. We have the piecewise constant interpolant, it goes to a limit, and we have the piecewise linear interpolant, which goes possibly to a different limit. We don't know a priori that these are the same. The other convergences are more or less standard. Okay, so let's see what we can do. So first we have to prove that this U bar and U hat are the same. So that can be done in the following way. You just look at the difference and you write it down what it happens. And then you take a test functions from your Hilbert space and you get this left-hand side. By Hölder, you can estimate it by the right-hand side. And because of that difference here, there remains a tau, and tau n goes to 0. So there the right-hand side goes to 0, which means if you also use that the functions of characteristic functions times an element from the Hilbert space is dense in this L2H, that you have a weakly converging limit. And because you already did know that in L infinity, L2 or H, you had already a limit, so they have to be the same. So we already do know that the limiting objects of the different interpolations are the same, which is good. So at least we are in the classical setting as for the Galerkin approximation. Okay, but there was this additional requirement in the Bochner pseudomonotonicity that on the time slices we get a weak convergence. So the first point you have to do here is you have your discrete solutions and you rewrite it with the help of the piecewise constant interpolation, and for the time derivative the piecewise linear interpolation as an equation now again as an evolution equation. And the next thing you do is you multiply this equation by a time-dependent function with compact support. You choose one point and your function should be equal to 1 around it. You use partial integration and you get this inequality. So it's just partial integration in time. And if you look at the terms, so we have V convergence of z. Z is a fixed function. It goes to 0. Same here. Because these are the same object, it both go to the same object and the right-hand side as well. So we go to 0. And what does it mean? It means that the object we are interested in, that this is a weakly converging, weakly Cauchy sequence in H, so it has a limit. This limit we call, because this limit, of course, a priori depends on the point where we were looking at. So we have a limit WS. But on the other hand, we did already know that, let's say, that piecewise linear interpolation converges weakly. No. If this is for every time, we can make a function which is time dependent, and therefore this U hat converges weakly in L2H. But we already do know that the same sequence has a different limit, so they have to agree again by the functions. And now we are almost done with this additional condition. The only point is we would like that here is not a hat but a bar, because we need that the piecewise constant interpolant converges pointwise in time. And we have only in the moments that the piecewise linear. And because that is clear, we have to do so because this information came from the time derivative. That's exactly the alternative. Aubin-Lyons use explicitly the time derivative, and here we just use the information coming from it. So, but that is also no big problem, because again, you can rewrite this difference between these two now, this time with the notion of the discrete time derivative, and you fix an m, little m, and you take any little n that is larger. And now we want to identify this in big spaces. These are the dual spaces, this difference. And because if the n is larger, we get immediately this trivial estimate. And using this identity, we get this expression. From the a priori estimates, we do know that including this tau n and the sum, this is bounded. So there remains some positive power of Tn. It goes therefore to 0 if Tn goes to 0. So what does it mean? This means that because now we have on the left-hand side, we have a strong convergence, and here are norms. So this means for almost all times, this object converges in this fixed Vm star, which is a very big space. So m is fixed and n goes to infinity. But on the other hand, we again do know that this converges weakly, and we have the density of this spaces. So therefore also it works nicely with the dual spaces. We can identify that this limit is also, if we on the left-hand side have the piecewise constant interpolance. Okay, so therefore this new additional condition, which was the Bochner pseudomonotonicity, is satisfied. It comes from the time derivative, which is not surprising, and it works for almost all approximation schemes you can think of. But the last point we did not use is we have to derive for the equation the pseudomonotonicity inequality. For that, we again start with our discrete equation, now written for the interpolants, take a test functions, use partial integration. And if we look at the right-hand side and on the left-hand side, all these quantities have limits. Maybe they are not the ones we really hope for, but at least we can pass to the limit in the equations. And so we want to identify the terms with a star as the right objects. But this inequality or this equality helps us already a lot, because if we take test functions which are 0 on these two places, which means these are C0 infinity test functions, then by the definition of the generalized time derivative, we do know that this function u bar has a time derivative, and it's exactly to this two quantities which we can see here. And this already means that the limiting object is in the right space. It has a time derivative, and moreover, this together we can show that we can evaluate the limiting object pointwise, and we can identify also That's a capital times the limit. Okay, so that was the first piece of information, that our limiting object is in the right space. But we also need to get the sign condition. For that, we again use the partial time integration, which is classical. We get if it would be a continuous solution, we would get here an equality sign. For the discrete time derivatives, they are always a little bit more complicated. So we get only a sign. And if we use in our discrete solution as a test functions the original solution, we get this equation. We use the partial integration formula, and we have this. And now we go to the limit and use on the left-hand side, we just lim sub always exists. Here we do know even the limit exists. Here also, because by the assumption. And here we have a weakly convergent sequence, but luckily here we have a minus sign, so the semi-continuity gives us that this is true. Using that, that's the same equality we have seen just derived. The last thing we have to do is we have a time derivative. So the u bar has this time derivative. We use this equation in the dual space, and use that we do know that this B star is the weak limit of our approximating sequence. So we get immediately that expression. And combining it with the other, we get the sign condition we were hoping for. So therefore, all assumptions of our pseudomonotonicity notion are fulfilled. We can conclude that the conclusion is correct, which means this is the upper lim inf condition, and just using the Minty trick, we can identify the limit. And therefore, we have shown that this fully discrete solution converges to a solution of our original continuous problem with the right regularity. Okay. So that means this new notion is even applicable to numerics. But if you have been careful listening, then you might have realized that I was speaking only about the typical example 1 now, because we were using a finite element approach and we had a p-heat equation, so that fits that together. If we are going to fluids, we have the divergence constraint and the finite element approach, and this divergence constraint does not really fit together very much. So the finite element solutions are not divergence free, but only discretely divergence free. So therefore, the previous setup does not fit with a really example which I have in mind, namely the P Navier-Stokes equation. So let's look again at this equation if our notion is so robust that it also works there. So here you see again the equations. The crucial point is the divergence constraint. So now we need a little bit more spaces. So we have the space where we want to work with this. Then we have the space without the divergence constraint, which is still nice. We have this H space and we have an L2. So now our discrete space is just the Sobolev space intersected with polynomials, where the space PM is just on each triangle or each simplex you have a polynomial, and but we still require that's a finite element approximation, so it's still conforming. And we need the space ZH, which is the space for the pressure, and therefore the space in which we can look for solutions is a space of discretely divergence-free functions defined there. The drawback is, as I already said, that this space where I can get a solution is a subspace of the space X, but it does not belong to the space where I want to get my solution. So previously we used a Galerkin approach, so we approximated by separability our targeting space from below. Now we are coming from the numerical size, and because these spaces VH are not a subspace, so we approximate our targeting space from above. And the question is, can we ensure that the limiting object belongs to the right space, again, to the targeting space, and is it good enough to combine it with our methods? So here we already see the previous setting is not good enough. So we have again to adapt our notion. So the idea is very simple, because in this finite element setting, we had the spaces where we want to work with, and we have the spaces which are still Sobolev spaces where our objects belong to. So we just double our Gelfand triples. So that is the one we want to work with, but that is the one in which our objects belong to. But they are nice because these are Sobolev spaces. The analog of that's the only difference between V and X is that it's not the divergence constraint. So therefore they have the same structure, they have the same norms, everything is nice, the same for the Hilbert spaces. But now, of course, you need an assumption on the spaces. If you want to take any sequence from above which goes somewhere, you cannot ensure that the limiting object is nice. So that now we need an assumption. So one assumption is there's a dense subset which can be approximated strongly by the objects we are working with. And if you have a sequence in the Bochner space with values in this space, and it converges in the space where all these objects belong, namely that's the space X, we cannot write V here, then the limiting object belongs to the right space. So these are again abstract assumptions, but one can easily check that the numerical spaces and choices for almost all pairs which are insubstable satisfy these conditions, so therefore they are realistic. Okay, so but what to do with our notion of Bochner pseudomonotonicity? We call it now quasi non-conforming Bochner pseudomonotonicity, so it becomes more complicated. The essential difference is the following. So since our objects we are working with don't belong in the spaces where we want to work, but only to some other ones, namely X and Y, we take everything in this bigger spaces where we do know that the finite element approximation belongs to. In order to even write this condition, we have to use here a projection, and otherwise nothing changes. So the point is, if we approximate from above, we take the bigger spaces to which it belongs and adapt our notion. Is this still working? The answer, let's see what, so for example, that the limiting object belongs to the right space comes from this approximation condition. So what do we need? We need, again, our operators are pseudomonotone, coercive, and have a growth condition. And that is, again, just to be applied to the steady case. And we get that the induced operator is then satisfies this new notion. And therefore, we can hope to prove, again, the convergence of this sequence. That was done together with Luigi Berselli and Alex Kaltenbach. So again, we take our problem, now the P Navier-Stokes equations. We assume that our sequence of spaces Vm satisfies this condition of the approximation properties. And we take discrete solutions satisfying now again our discrete equation, the discretization of our equation. But now, of course, in the bigger spaces, because on these objects only belong there. We can show again by Brouwer's fixed point theorem that it exists, and we just require that the operator satisfies this condition. When we have objects and we take the piecewise constant interpolant, and the statement is the same. Each weak accumulation point is a solution of the original problem. And this time it's applicable to the P Navier-Stokes equation. And essentially each insubstable finite element setting works. So what is the difference? I don't go to all the details, but just tell you, before we worked in the spaces V and H, now we replace all these spaces by X and Y. It works exactly in the same way. We use these approximation conditions of the spaces to ensure that the limiting object belongs there where it should belong. We get a priori estimates, of course, again, also in these big spaces with appropriate sequences. And now we have just to repeat the same steps. I don't want to do it. I just want to explain it on the new condition which we needed. This is the projection converges in the right way. So what you do, you start with the object you want to get an information about. You test it with any object from the space H. By the definition of the projection, this is the same as that. Now it's in the space Y. You add and subtract on the right-hand side or on the test function argument this sequence, which we do know that they exist and is strongly converging. And now look at the first term. It's in the space V and A dual. It converges to 0, and that is bounded. And here we have a weakly converging sequence, and that is strongly converging, and everything works, and the method can be applied. Okay, which is very nice. So we got to 0, and that is the condition you need, and you can conclude the result as before. So, okay, that was this very complicated name, quasi non-conforming Bochner pseudomonotone. So why quasi? Quasi because the non-conformity was just because of the divergence constraint. Our finite element space was still, let's say, continuous, at least on the intersection of two triangles. But in the numerical community, there are a lot of effort in the moment to avoid this, to just work on each triangle. You take a polynomial and you don't have any continuity condition to the next triangle. So each triangle can do what it wants. So again, same equation. And this method is called discontinuous Galerkin method. Discontinuous because it's not continuous on the triangle faces. We need even more spaces. So we need the space where we want to work with. We need the space where we were hoping before that it should work. The same is here. But now we need an additional, even a sequence of discrete spaces. This is a space which is on each triangle a Sobolev function, but it has no interaction with the next triangle and the Sobolev. So it's a discontinuous object. Here we need pressure space, and we can again write down a discontinuous divergence-free discrete space. Okay, so what is the situation now? It becomes worse and worse because our space where our solutions will belong only to this sequence, H-depending sequence of discontinuous Sobolev spaces. They don't belong even as before to the Sobolev space, but the only thing where they really belong to is the space Y, which is the L2 space. So this means what we have lost before, the large space still was a Sobolev space with information about the gradient. Now the large space where everything belongs to is a Lebesgue space, but our limiting object should again be a Sobolev function. So again, question, does it work? You guess already the answer. So first of all, it does not fit the previous setting. Again, we have to adapt. And now the trick is, before we had one Gelfand triple where we wanted to work with and another one where we could work in. But now this one is now a sequence of spaces of Gelfand triples. Essentially, we see again the norms are the same, but here this is reflecting the fact that we have control in this space only about the Lebesgue space and not about gradients. Again, we require that we have an approximation property, which is exactly the same. Only one has to be more careful because now we don't have one space in which we can formulate convergences. So therefore, one has to be careful. And for example, you see here, you have an object in the space and only the norm converges. We don't say that it is this sequence Vn is converging in one fixed space. And similarly here, we have a sequence in Bochner spaces with n-dependent targeted. We can't speak about convergence, so therefore we have only that the supremum is bounded. And if we have a subsequence and a limiting object in the spaces where we can work with, then again, this is the right object. But the information we can only get in is the space Y, because that is the only space where all this DG Sobolev spaces belong. Okay. So what are these DG gradients? Essentially, it's a classical gradient locally on a triangle plus the jumps between two triangles, because if there's no interface before, so it's a jump and you interpret that in that way. And again, you can generalize this Bochner pseudomonotonicity to a non-conforming one. So now we work with the sequence of spaces. If you look at the operators, now for the first time, the operator really depends on the approximation parameter. So therefore, we have a sequence of BNs. And it is Bochner pseudomonotone with a limiting object. Again, we have the same conditions. And one has to be now very, very careful, because the targeting space is now not fixed. It was before, it was an X, now it's an XN. One has to be careful. And again, our approximation procedure gives us this limiting object is in the right space. And so we want to look at the same problem. We take an approximating sequence. We can solve the discrete problem. Now, of course, in a sequence of spaces, we again just have to require that our operator satisfies these three conditions. But of course, we have now also our operators Bn, which satisfies something which is similar. I don't want to be specific here. We have solutions. We take the piecewise constant interpolants. And again, each weak accumulation point is a solution. And again, essentially, all DG formulations for the P Navier-Stokes and other equations satisfy these abstract conditions. So idea is very similar. So we just replace before for the original solution, we had this V, then we replace it by X, now we replace it by XN. And if one is careful, again, these approximation properties shows that the object is in the right, the limiting object is in the right spaces. We have convergences now only in the space Y, so no information about the gradient. But in the very large spaces dual here, we can take the identity, the dual space, so which is a restriction operator. It still converges, that we can formulate it really in the space. And again, let me explain the setting. So the new condition, essentially it works in the same way. We have in a space H, by the definition of the projection, we are in Y. We add this sequence from the space of this dense set, and the first term converges due to that, and the second also in the same way. So it's exactly the same. We can go to 0. So, okay. That is all I wanted to say, just to recapitalize. So the difference between pseudomonotonicity and Bochner pseudomonotonicity is it is fitted to evolution problems, so it takes into account the information you get from the time derivative, and it seems that it is a very natural notion. This gives you exactly the same setup as in the elliptic case, now in the parabolic case, and it is very robust. You can use it for Galerkin approximation in an abstract way. You can take it for Rothe-Galerkin approximation in finite element spaces or even in DG spaces. So, and I think there are other things. For example, some people know that I'm working in this variable exponent spaces. Also there, exactly this fits. It can be generalized to that. So it seems to be probably the right notion in the parabolic. So thank you very much.
Thank you very much for your nice talk. So we have time for some questions, remarks. So first here in Prague, please.
So thank you for your really nice talk. So as I understood, so you presented this really nice formalism to solve more compactly all this problem with this concept and notion about Bochner pseudo monotonicity. And looking into the details, I can see that there is, of course, a lot of the techniques you used for solving the problem in a non-cylindrical domain. And this formalization can be used to also directly explain the way to solve like non-cylindrical domain, because you say that you were working on the variable power bound space, and also for time-dependent domain. Is this working the same way, maybe?
Probably. So on the, let's say, time and space-dependent exponents, we looked already a little bit into that, and it seems that it works. But also this, as you said, this variable domain, so like fluid structure interaction problems. I think also, again, something like this non-conforming, because you can embed this domain always in a big cylinder and work on that. You just have to find the good penalization or so I'm optimistic that it could work, but we did not check any details for this variable domains, but we checked some details for variable exponents. But if I'm right, so I guess one can do it, but nothing has been done until now.
Some further questions? Maybe just a short question. So it works all for, say, in 3 dimensions for p larger than 11/5, yes?
Yeah, so that is just the case of Lyon from 69, so 11/5 and 2 dimensions larger than 2. So this is just, so the motivation was in the beginning to save this 5 pages to show that my approximating sequence exists. Now we can just quote one theorem, check 2 conditions, and it's done. And then you can concentrate on the real new aspects of the theory. It does not give any Lipschitz truncation, or it cannot work for that settings. This is clear.
Okay. Yes.
Can it be used also for hyperbolic problems with this pseudomonotone technique, or is it more difficult to estimate?
Yeah. Again, I have to say we did not look at the hyperbolic setting. I think the structure is a little bit different, because in the hyperbolic setting, so if you want to go for a nonlinear problem because of the second time derivatives, for example, it has a different structure. And I do know that there are some results about, let's say, P wave equations, but it is a different version of the pseudomonotone. So it's a maximal monotone perturbation of a pseudomonotone operator. And in a sense, I'm optimistic that it could work, because one of this intermediate step I did not spoke about today was exactly that you use that abstract theorem of Brouwer, which is, as far as I know, applicable to hyperbolic settings. So it could be, but I don't know.
Okay, still some questions here in the audience. Yes.
Thank you for the lecture. So you discussed the finite element approach, where you discretize both. You discretize both time and spatial domains. Is there any benefit of considering a problem where you have continuous time but discretized space?
It depends on your problem, of course. But for example, if you are looking at, let's say, the Navier-Stokes equations, and you might know that if you want to get proof convergence rates, that you need additional regularity. And for example, the natural regularity for these equations is still suboptimal. It's not proved, and therefore you cannot apply it. But if you have space and time discretization, the only object you want to approximate is your continuous solution. And for that, you can assume something, some regularity you require, and you can show that your method has a convergence rate. If you use, let's say, space discretization and continuous in time, then you have an intermediate problem, and you have to show that this intermediate problem inherits some regularity, and because that is not known, you cannot use it. So the advantage would be of a full discretization that you have the possibility to assume regularity on the continuous problem. Maybe later somebody is able to prove it, but you can nevertheless get some better information out of it. But also either this continuous in time or continuous in space and discrete in time, both are possibilities. It depends what you want to prove.
Other questions here in the audience? Someone online? Okay, seems there is no question in the online audience. So let's thank the speaker once more. And that's the end of today's seminar.